Hi. So in the previous video, we just saw that the force, the universal law, Newton's universal law of gravitation, where he equated force to a gravitational constant times the mass, product of the mass of both the objects divided by the square of the distance, right? And we did say that this was calculated. I mean, on a laboratory setup, this was actually calculated much later, and the gravitation force, the constant came out to be this value. So this is the constant, which is 6.67 times 10⁻⁸ meter cube kilogram -1 to the power of -1 and seconds per second square, right? So this is a constant, and we'll be using these in as we solve some of the problems. So typically recap where we left last time. So we spoke about the two forces, the centripetal force and the centrifugal force of any object that takes a circular path around another object. So in this case, we took an example of the moon revolving around the Earth, or into the example of a stone that is tied to a string which you rotate around you. And we saw that how the centripetal force, which is the force that is acting towards the center, and the corresponding the reaction force is the centrifugal force that acts on the object to push it outside. And we saw that example in the merry-go-round, right? When you are in a gathering or in a festival, right? So which you see in a festival. So just to close that, think of what will happen, right? Say take the scenario of this. Take the scenario of having a string that has a stone tied to it, and then you are rotating that around you. What would happen if you suddenly leave that string? Or in other words, what would happen if the object loses the influence of that force, right? What will happen there? Now, if you really think about it, in this case, while as long as the object is under the influence of that centripetal force, it will take a circular path. But let's say you drop it at this point, right? At this point, you drop that, you leave the string, which means that the object is no more under the influence of that force, and it's likely to take the straight path from here, right? In fact, it's likely to go somewhat like this, right? So that is a path that it will take. So it will take a path that is tangential to the circle, right? So this if you consider this as a circle, and this is considered as a tangent to that circle. So this is how the object will leave the moment it becomes the moment it is no more in the influence of that centripetal force, right? Now, this is something that we observe in many games. If you see in Olympics, that there are games like discus. If you see the field events specifically, there are games like throwing a hammer, or throwing a discus. If you really see the hands of the discus thrower, it exactly they would exactly mimic this behavior. They would do this, right? So if you really see in the field, if you observe closely, the field setting of a discus thrower, there will be a place where the player would stand, and the field will be sort of a V-shaped field, and where they would measure the distance. They are allowed to throw the disc only between these two areas. And you have all the spectators, sitting on the either side, right? So this is how the track would be, and this is how the whole track would be. And here is where you will see all the runners. And the discus player is likely to release, if he or she is a right-handed discus player, he or she would release the disc somewhere at this point, so that it takes the path tangential to the circle and falls somewhere here, right? So the discus player would do a circle, right? I mean, he or she would do a circle, and then he would release it somewhere here, so that it takes a path tangential to that circle, and then it lands here. And he has to be very careful there. And in case he lands it somewhere here, right? By mistake, if the discus player lands it here, releases the disc here, it is likely going to take a path like this, and it might hurt somebody, right? So that is why, right? So that is why if you observe, there will be a lot of protection between, in one side of it. There will be possibly a net or some protection so that it doesn't come out of that, and the disc can only take a path it through this opening onto the field, right? So just wanted to give this example so that it is clear to you. So universal law of gravitation is a very important discovery by Newton, and this explained quite a few things, right? Primarily, it helped us explain why it helped us explain the movement of the moon. It helped explain the movement of the various planets. It helped explain why an object always falls onto the Earth, right? Gravity, and it also explained why the cause for high tides and low tides, right? When the moon is closer to the Earth, there is a variation that you'll observe, right? With the tides, and Newton. It's all because of Newton's law of Newton's law of universal law of gravitation. So it was very useful and one of the most important discoveries in physics. So now let's focus on the gravity that is experienced by objects around the Earth, right? Now, when we say an apple is falling on the Earth, right? Let's take this to be the Earth, and let's take this is the apple, right? And when we say that an apple is falling onto the Earth, we say that it is because of the force between the apple and the Earth, right? So, per Newton's law of gravitation, it is a force. The Earth's mass and the apple's mass would result in a force between them, so that it would act on each of them. And because the apple is of a smaller mass, it will end up moving towards the Earth, right? So there is a force between them, and can we and that force is always acting, right? It is not that a force the force gets applied just at one moment and then it is lost. No, the force is exerted, or the force is influenced by the apple and the Earth until the moment it touches the Earth, right? So there is a constant application of that force, whatever it is, right? And we know from the earlier chapter that when the force is constantly applied, that object undergoes an acceleration, right? The velocity keeps changing, right? So in the case of Earth, can we try to quantify that? What is that acceleration? Because that force is always constant. For any object that falls onto the Earth, that goes through an acceleration, right? Because that force that is influenced by both the objects happen all the time until they come to contact, right? So let's try to quantify that. So now let's consider this to be object A, MA, and let's consider the mass of the Earth to be ME. Now I'm going to consider the distance between the Earth. Let's consider let's go. Let's take this as let's consider this to be the center of the Earth, and let's consider the distance between the center of the Earth and the center of the object to be D. Now this means that the force that is between the object, this could be your apple, and the Earth is if you call that F, that force is equal to the gravitational constant Ma times Me over D square, right? So in this case, the D is obviously the distance between the center of the Earth and the center of the object, which is closer to you. Now, how do we quantify this? How do we expand this force? So we know that force is per Newton's second law. We know that force is mass times the acceleration of that object. So if you take this object as mass, the mass of the object, right? The force experienced by the apple is ma times. Let's call the acceleration experienced by this. That's what we're trying to calculate. But let's say you take let's call it g for now, right? is equal to G times the capital G, right? So the small g is what we're calling as the acceleration experienced by by the apple towards the Earth, and the capital G is the universal law of the gravitation constant, which is this, right? So G times ma times me over d square. Now, if you cancel this out, which means that your G becomes equal to your gravitational constant times me over d square. Now, if you really see this equation, you can actually find a value for this, right? Because you know the value of G, which is your gravitational constant, and me is the mass of the Earth, and we have an estimate for the mass of the Earth, and d square is the distance between the center of the Earth and the object. For objects that are close to the Earth, when I say close to, it can be few meters above the Earth, right? In that case, this distance is negligible as compared to this whole distance. So you can approximate this distance for objects that are close to the Earth. You can approximate that actually you don't have to really consider the actual distance between the center of that object to the Earth, but rather you can just take the radius of the Earth, right? So if you replace this with the radius of the Earth, you will find that this rate of acceleration comes down to be around 9.8 meters per second square. And this is the gravitational constant for the Earth. And whenever an object, so when we say an object falls, it is accelerating at this particular rate. Near to the Earth, an object would accelerate at this particular rate, which is 9.8 meters per second. And we call that force as the gravitational force. And whenever an object that is under the influence of the gravitational force is considered to be we call it to be falling freely, or it's a free fall, right? Whenever it is an object that is under the influence of the gravitational force, we call that as the object undergoing a free fall, right? Under the influence of gravitational force. So, so if there is one other thing, if you really see this equation, so all these came in much later, during the times of Isaac Newton, and much later to that, right? But one nice thing, cool thing that you see here is, while you were trying to derive this equation, derive the value for the the gravitational force, or the acceleration due to the gravitational force, when we are trying to quantify G, we saw that G equates to the gravitational constant times the mass of the Earth over the diameter, over the distance square, and d we took it as the radius of the Earth, right? And for every object that is fairly closer to the surface of the Earth, when I say fairly closer to the surface, it can be a few meters or even hundreds of meters, where the force is still strong, right? I'm not talking about the distance over the Earth. As you move farther, we know that when you go closer to the Moon, that object will become more will get more influence towards the Moon, right? I'm not talking about that high distance, but at least a few hundred meters above the Earth, it would still be under the influence of the gravity of Earth, right? So for all those objects, you can consider, you don't have to consider the distance between that center of that object to the center of the Earth, but rather you can just take that distance to be, you can approximate that distance to be the radius of the Earth only, right? So when you take that logic, you will see that every object accelerates at the same speed, because this value of G is independent of the mass of that particular object, because we have already cancelled it out, right? So which means that every object falls at the same rate, and this is what Galileo was trying to prove. If you remember in our earlier videos, Galileo tried to break this myth that which many people had at that point in time, that heavier objects tend to fall sooner onto the Earth, but than the lighter objects, and this is exactly what we're seeing, as proven mathematically, right? It is irrespective of the mass of the object. So this value of G, which is the acceleration due to the gravitational force of Earth, is not dependent on the mass of that particular object. It is only dependent on the mass of the Earth times the distance squared. So this is another thing which Galileo once, Galileo didn't, even before all these were proposed by Newton. Galileo had already, felt this truth, and that's what he was trying to tell the world. Now this whole thing, if you really equate, because this is acceleration through the gravitational force. We all recall the three laws of motion. And we can all of them will apply here. Just that in this case, the motion has happened in a vertical direction, right? We always saw the examples of objects moving in the horizontal direction, but it doesn't matter. In this case, when an object is in free fall, it takes a vertical path, right? And the same laws hold good. So the original equations were, if you were to just recap the original equations, the first law was V is equal to U plus AT. There, V was U was the initial velocity of the object, and V was the final velocity of that object, and it was undergoing an acceleration of A for and T was the elapsed time, right? The second equation was yes, the distance is equal to S is equal to UT plus half times AT square, right? So this was the second equation. S is the distance or the displacement. I mean, S is the distance, but for an object that is moving in a straight path in whichever direction, horizontally or vertically, it becomes the displacement, right? And the third one was 2AS is equal to V squared minus U squared. So these were the three laws of motion, and for any object that is on a free fall or that is under the influence of gravitational force, the gravitational this acceleration would apply here. So we can write the same thing as V is equal to U plus GT. You can replace A, the occurrence of all A, with G, because that is the acceleration experienced by an object, right, closer to the Earth. So S equals UT plus half GT squared, and 2AS is equal to V squared minus U squared. So that is the law of the three laws of motion restated for the gravitational force of the Earth. So let's stop here, and then we'll take this. We'll discuss a few other concepts of gravity in our next video, and before we move on to the force that is experienced in fluids.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.